Hello students, welcome back to my channel. In this video, I am going to discuss in detail about the isomerism. Generally, isomerism is observed in the compounds containing covalent bond. That means organic compounds exhibits isomerism. The compounds having same molecular formula but different physical or chemical properties are called isomers. And the phenomenon is known as isomerism. Isomerism is classified into two types. One is structural isomerism and the second one is stereoisomerism. Again, structural isomerism is classified into 5 categories. One is chain isomerism, second one is position isomerism, third one is functional isomerism, fourth one is metamerism, and the fifth one is tautomerism. Coming to stereoisomerism, it is again classified into two types. One is configurational isomerism and the other one is conformational isomerism. Configurational isomerism arises due to the breaking and reforming of the bonds, whereas conformational isomerism arises due to the rotation around the C single bond C. Coming to the conformational isomerism, again it is classified into two categories, one being geometrical isomerism and the other one is optical isomerism. Is it clear about the types of isomerism, students? Next we will discuss about the structural isomerism. Structural isomerism arises due to the difference in the arrangement of atoms or groups within the molecule. That means structural isomers will have same molecular formula, but there will be some difference in the structural formula. Let us see chain isomerism. Chain isomerism arises due to the difference in the arrangement of carbon atoms within the given molecule. So, in order to exhibit chain isomerism, minimum 4 carbon atoms are required. Let us see if the compound contains only 3 carbon atoms or 2 carbon atoms or 1 carbon atom, whether it exhibits chain isomerism or not. If the compound contains only 3 carbon atoms, there will be no change in the arrangement of carbon atoms. That's why compounds containing 1 or 2 or 3 carbon atoms will not exhibit chain isomerism. So, minimum how many carbon atoms are required to exhibit chain isomerism, students? 4 carbon atoms are required. So, let us consider the chain isomerism in the case of alkanes. So, let us consider one best example, that is butane. What is the molecular formula of butane, students? That is C4H10. So, by using this molecular formula, we can write butane as CH3, CH2, CH2, CH3. So, it is N-butane. So, what is the name of this compound? N-butane. And how to write the chain isomer for N-butane? Let us change the position of carbon atom in this molecule. Then we can write its chain isomer as CH3, CH, CH3, CH3. If you carefully observe these two compounds, they are having the same molecular formula, but there is some difference in the arrangement of carbon atoms within the molecule. So, these two are called as the chain isomers. Can you name the second compound? Yes. How many carbon atoms are present in the parent chain? 3. So, it is called as propane, and in the second position methyl group is present. So, it will be called as 2-methyl propane. Is it clear about the chain isomers present in butane? Let us see few more examples. In the case of alkenes, for example, let us consider 1-butene. Okay, so it can be written as CH3 single bond CH2 single bond CH and double bond CH2. Can you write the corresponding chain isomer? Chain isomer means there must be some change in the position of carbon atoms. So, let us write the corresponding chain isomer. CH3 single bond C CH3 double bond CH2 is the corresponding chain isomer. Can you name this compound? So in the second position methyl group is present. So it will be called as 2-methyl propene. Is it clear, students? So for the given compound, it is possible to write the chain isomers if the compound contains at least 4 carbon atoms. Let us see one more example. The molecular formula is C4H10O and hence the corresponding structure can be written as CH3, CH2, single bond CH2, single bond CH2OH. That means it will be called as 1-butanol. So what is the name of the compound? Yes, it is 1-butanol. You just try to write the corresponding chain isomer. You just try to write the corresponding chain isomer. You just change the position of carbon atoms. So it will be CH3, CH, CH3, CH2OH. Can you name this compound? In the second position, methyl group is present. And what is the functional group? Alcohol. So it will be called as 2-methyl propanol. Is it clear about the chain isomerism? And remember that depending upon the number of carbon atoms present in the given alkanes, it is possible to write the number of chain isomers. So the starting alkane is butane, that is C4H10. So in the case of alkanes, it is possible by knowing the number of carbon atoms present in the given compound, we can write the number of chain isomers by using the formula. If the given alkane is C4H10, then we use the formula 2 power n minus 4 plus 1 to know the number of chain isomers. So in this formula, it will become 2 power 0 plus 1. That means how many isomers are possible? Especially chain isomers, 2 chain isomers are possible if n is equal to 4. Coming to the second alkane, here how many carbon atoms are present, students? C5. So in this formula, n is equal to 5. So 2 power 5 minus 4 plus 1. That means 2 power 1 plus 1. So how many chain isomers are possible, students? 3. So coming to the C6H14, here n is equal to 6. So it will become 2 power 6 minus 4 plus 1 and hence 2 square plus 1. Totally 5 chain isomers are possible. And coming to the C7H16, here n is equal to 7. So it is 2 power 7 minus 4 plus 1. That means 2 cube plus 1. So on the whole 9 chain isomers are possible. So 2 power n minus 4 plus 1 formula is applicable if the value of n is equal to 4 to 7. But if n is equal to 8, we have to use the formula 2 power n minus 4 plus 2. So in this case what happens? N is equal to 8. So 2 power 8 minus 4 plus 2, that is equal to 2 power 4 plus 2 and hence the corresponding chain isomers are 18. If n is equal to 9, then we have to use the formula 2 power n minus 4 plus 3. Here n is equal to 9 and hence 2 power 9 minus 4 plus 3, that is equal to 2 power 5 plus 3 and hence 35 chain isomers are possible. And if the value of n is equal to 10, then we have to use the formula 2 power n minus 4 plus n plus 1. Here n is equal to 10. So 2 power 10 minus 4 plus 10 plus 1 and hence it is equal to 75. Is it clear, students? So simply by knowing the number of carbon atoms present in the alkanes, it is possible to predict how many number of chain isomers are possible. Let us move on to the position isomerism. So position isomerism, arises due to the difference in the position of the functional group or even the position of the multiple bond or due to the difference in the position of the substituent. Let us see few examples. If the molecular formula is C3H7OH, we can write the structural formula as CH3 single bond CH2 CH2OH, and hence it is called as 1-propanol. So, in case of position isomerism, there must be change in the position of the functional group. Will you write the positional isomer for 1-propanol? You have to change the position of OH group. So, we can write as CH3 CH OH CH3. Can you name this compound? The OH group is present in the second carbon atom and hence it is called as 2-propanol. So these isomers are due to the change in the position of the functional group. Hence they are called as position isomers. Clear, students? Let us apply the same principle to C4H8. So by using this molecular formula, we can write the structure of 1-butene as CH3 single bond CH2 single bond CH double bond CH2. It is 1-butene. You try to write the position isomer for 1-butene. Simply by changing the position of the double bond, we can write the corresponding position isomer. That is CH3 single bond CH double bond CH CH3. Can you name this compound? In the second position, the double bond is present and hence it can be called as 2-butene. Is it clear about the position isomerism, students? Now let us move on to the functional isomerism. So what do you mean by functional isomerism? Functional isomerism arises due to the difference in the nature of the functional groups present in the given isomers. That means the two isomers differs in the nature of the functional groups. Let us see one example. Molecular formula is C2H6O. By using this molecular formula, we can write the structure of ethanol as CH3 single bond CH2OH. Okay, so can you write the functional isomer for this compound? Yes, you just change the functional group. So the corresponding functional isomer can be written as CH3OCH3. It is either and it can be called as dimethyl ether. From this example, it is very clear that the functional isomer of alcohol is the corresponding ether. Okay, students, is it clear about the functional isomerism? Let us see few more examples for the functional isomerism. If the molecular formula is C3H6O, we can write the structure as CH3 single bond CH2 CHO. That means 1-propanol. Here the functional group is aldehyde. So can you write the corresponding functional isomer? So keto form is the functional isomer for the aldehyde. That is the hint. Okay, by using that hint, you try to write the corresponding functional isomer. So the corresponding functional isomer can be written as CH3 single bond C double bond O CH3. Here the functional group is keto. In the previous one, the functional group is aldehyde. So aldehyde is the functional isomer of ketone. Can you name this compound? It can be called as it can be called as propanone. So what is the name of this compound? Here 3 carbon atoms are present and the functional group is ketone and hence it can be called as propanone. Is it clear about the keto and aldehydes having functional isomers? Next, let us see two more examples. Here, propanoic acid is given. Remember that acid is the functional isomer of the ester. Will you write the corresponding ester structure? Yes, it is CH3 COOCH3. Can you name this compound? Yes, it can be named as methyl ethanoate. So, acid is the functional group of the ester. In the similar way, when we consider the methyl nitrile group, the corresponding functional isomer will be CH3NC. That means it is the isocyanide. It can be called as methyl isocyanide. So from this example, it is very clear that isocyanide is the functional isomer for cyanide group or nitrile group. Is it clear about the functional isomerism? Next, let us discuss about the metamerism. So, how metamerism arises? It arises due to the difference in the nature of alkyl groups attached to the same functional group. Here, there will be no change with respect to the functional group. The only change is with respect to the alkyl groups attached to the functional group. Let us consider diethyl ether. So, just by changing the nature of the alkyl groups, we can write the corresponding meta-isomer. Can you write? You just try to write the meta-isomer for diethyl ether. So, you just change the alkyl groups. So, in the case of ethyl functional group, that is ethyl group, you just write one methyl group and one propyl group. Then there will be no change in the molecular formula, but here the only change is with respect to the alkyl groups. Can you name this compound? It can be called as methyl propyl ether. Okay students, it is very clear about the meta-isomerism. Let us see one more example. Here which compound is given? Dipropylamine. So here what is the functional group? Amine group. So just you change the alkyl groups. Here propyl groups are the alkyl groups. Then how to change? You just put one ethyl group and then butyl group. Then it becomes butyl ethyl amine. So these two are called as the meta-isomers. That is about the meta-isomerism. Let us move on to the tautomerism. So tautomerism is very interesting. So coming to the tautomerism, here always we prefer keto-enol tautomerism. In this case what happens? Let us see. Always the isomers will be present in equilibrium. So the keto-enol tautomerism arises due to the migration of alpha hydrogen towards the keto group. So in this compound, what is the functional group? Keto group. So if the adjacent carbon atom contains at least one hydrogen, then we can write the corresponding enol form. En plus ol, and hence it is called as enol form. And here the functional group is keto group, and hence it is called as keto form. What is the requirement to exhibit keto-enol tautomerism? At least one hydrogen should be present on sp3 hybridized alpha carbon atom. So the alpha carbon atom should be sp3 hybridized and it must contain at least one hydrogen atom to exhibit keto-enol tautomerism. Is it clear, students? So you just remember this condition. So let us examine whether the given compounds exhibits keto-enol tautomerism. Here what is the name of this compound? This is cyclohexone. Okay, cyclohexanone. You have to examine whether cyclohexanone exhibits keto-enol tautomerism or not. So these two are adjacent carbon atoms, and let us consider it as alpha carbon atom, and it is also alpha carbon atom. Here the carbon atom is sp3 hybridized and it contains hydrogen atoms, so it exhibits keto-enol tautomerism. Let us try to write the enol form. How to write the enol form? You just migrate the alpha hydrogen to the adjacent group, that is COH. Okay, with the result what happens? In the adjacent position the double bond will be formed. So it is the keto form and the corresponding one is called as enol form. Is it clear, students? Let us see few more examples whether they exhibits keto-enol tautomerism or not. What is the necessary condition? Alpha carbon atom should be sp3 hybridized and it must contain at least one hydrogen. So here the keto group is present. These are the alpha carbon atoms. Still they are having hydrogen atoms. So this compound exhibits keto-enol tautomerism. Coming to the second compound. Here it is the keto group and it is the alpha carbon atom. Remember that here it is sp2 hybridized. So this compound will not exhibit keto-enol tautomerism. Coming to the third compound. Here two alpha carbon atoms are present and this alpha carbon atom is sp3 hybridized. Still it contains hydrogen atoms. So this compound exhibits keto-enol tautomerism. Coming to the fourth carbon atom. Though it contains two alpha carbon atoms, both of them are in sp2 hybridized state and hence this compound will not exhibit keto-enol tautomerism. Coming to the fifth compound S, the alpha carbon atoms are sp3 hybridized, still they contains hydrogen atoms, so this compound exhibits keto-enol tautomerism. And coming to the cyclic structure, here two alpha carbon atoms are present and hence these alpha carbon atoms also contains hydrogen atoms. This compound also exhibits keto-enol tautomerism. Is it clear about the tautomerism? Especially keto-enol tautomerism. Next, let us discuss about the stereoisomerism. So, stereoisomerism means they have same molecular formula, even the structural formula is same, but there will be some difference in the arrangement of atoms or groups in space. Is it clear? So again stereoisomerism is classified into two types. One is configurational isomerism and the second one is conformational isomerism. Coming to the configurational isomerism, here the isomers are interconvertible only by breaking and reforming of the covalent bonds. Is it clear? So in the case of configurational isomerism, the two isomers are interconvertible only by the breaking and forming of the covalent bonds. Again, these configurational isomers are classified into two categories. They are very interesting. One being geometrical isomerism and the second one is optical isomerism. Coming to the geometrical isomerism, this geometrical isomerism arises due to the restricted rotation around the double bond, or it can also be observed in the case of ring structures. That means we can observe geometrical isomerism in four different types of compounds. Namely, whenever the double bond is present between the two carbon atoms, we can observe geometrical isomerism. If the double bond is present between carbon and nitrogen, we can also observe the geometrical isomerism. If the double bond is present between the two nitrogen atoms, then also we can see geometrical isomerism. Even the cycloalkanes exhibits geometrical isomerism. The first and foremost important condition is, in the case of geometrical isomers, here always different atoms or different groups must be attached to the doubly bonded atoms. If it is C1 carbon atom, A and B are different atoms or groups, and we have to examine the second carbon atom also. Here also different atoms or different groups are present, and hence this compound exhibits geometrical isomerism. So how to examine whether the given compound exhibits geometrical isomerism or not? You have to examine each atom. On each atom, two different atoms or groups must be attached. Let us see this example. In this example, different atoms are attached on the first carbon atom, and also on the second carbon atom, different atoms are attached. If the similar groups or atoms are present on the same side of the double bond, the corresponding isomer is called as cis isomer. Clear? So, if the similar groups are present on the same side of the double bond, the isomer is called as cis isomer. If the similar groups are present on the opposite side of the double bond, the corresponding isomer is called as trans isomer. Is it clear? If the similar groups are present on the opposite side of the double bond, the corresponding isomer is called as trans isomer. Students, is it clear about the geometrical isomerism? Let us examine whether the given compounds exhibits geometrical isomerism or not. So coming to the first example. So in order to test whether the given compound exhibits geometrical isomerism or not, we have to examine the atoms or groups present on each atom. So in the first carbon atom, different atoms are present. On the second carbon atom also, the two atoms are different. So it exhibits geometrical isomerism. In addition to that, here the similar groups are present on the same side of the double bond, and hence it can be called as cis form. Can you write the trans form? You just rotate the molecule around the second carbon atom. That means there will be no change with respect to the position of atoms on the first carbon atom, and you just change the position of atoms around the second carbon atom. You just rotate the second carbon atom. Then what happens? The similar groups will be present on the opposite side of the double bond, and hence it can be called as trans form. Is it clear about the cis and trans forms? Now simply let us examine whether the given compounds exhibits geometrical isomerism or not. Here in this compound, two different atoms are present. Here also there are two different atoms, and hence it exhibits geometrical isomerism. This is about the C double bond C compounds, and let us examine if the double bond is present between carbon and nitrogen, what happens. Nitrogen can have only one atom, no need of examining the nitrogen. You have to test carbon atom. Hence here also the two atoms or groups are different, and hence it exhibits geometrical isomerism. Let us see few more examples. Here in this case, on the first carbon atom, the atoms are different, but coming to the second carbon atom, methyl, and it is also methyl group, so it will not exhibit geometrical isomerism. And coming to the second example, here on the first carbon atom, different atoms are present, hydrogen and deuterium, and on the second carbon atom, methyl and ethyl groups are present, and hence it exhibits geometrical isomerism. Is it clear about the geometrical isomerism? Let us see if the double bond is present between nitrogen atoms, how to test the presence of geometrical isomerism. Here we have to consider the presence of lone pair electrons on the nitrogen. So here The first nitrogen contains lone pair of electrons and the group is methyl group. On the second nitrogen also lone pair of electrons and methyl group are present. So these two are different and these two are different. And can you examine what is the nature of this isomer? Similar groups are present on the same side and hence it can be called as cis form. Can you write the transform? You just rotate around the second nitrogen. Then what happens? No change in the position of first nitrogen and you just rotate around second nitrogen atom. Then the methyl group is present here and the lone pair of electrons are present here. So similar groups are present on the opposite side of the double bond and hence it is called as the transform. Is it clear about the cis and transforms? In the case of compounds containing nitrogen, double bond nitrogen. Okay, so you just examine the second compound. Here also different groups are present and hence undoubtedly whenever the double bond is present between two nitrogen atoms, they exhibits geometrical isomerism. And finally we have to examine what type of compounds exhibits, especially cycloalkanes, whether they exhibits geometrical isomerism or not. So if you carefully examine this cycloalkane, here acid groups are present on the same side of the double bond and hence it can be called as cis form. So these cycloalkanes also exhibits restricted rotation around this ring. And can you write the transform, corresponding transform? Yes. No change in the position of atoms or groups present around the first carbon atom. And coming to the second one, you just rotate around the ring and hence acid group is present above the ring and hydrogen will be present below the ring. Similar groups are present on the opposite sides of the ring and hence it is called as transform. Is it clear? How to examine cycloalkanes will you know? Okay. Next, let us apply to the second compound. Here the two atoms are different on this carbon atom and also on the second carbon atom also. These are two different atoms and hence it also exhibits geometrical isomerism. When you compare or when you consider cyclopropane, it will not exhibit any geometrical isomerism. Why? Here similar groups are present on each and every carbon atom. So it will not exhibit any geometrical isomerism. Is it clear about the geometrical isomerism in different types of compounds? Next, let us discuss in detail about the optical isomerism. Remember that in order to exhibit optical isomerism, a compound is supposed to have non-superimposable mirror images. So, what do you mean by non-superimposable mirror images? Let us consider a simple example. So, it is the basic compound. Here, one chiral carbon is present. Now, tell me what do you mean by chiral carbon? So, if four different atoms or groups attached to the carbon atom, thus that carbon is called as the chiral carbon. So, here different atoms or groups are attached to the center carbon and hence it is called as the chiral carbon. And we can write the mirror image. You just place the mirror and write the mirror image. And remember that this mirror image is non-superimposable and hence this compound is optically active. Yes. So, if the compound contains non-superimposable mirror images, then the corresponding compound will be optically active. Okay. So, in case of optical isomerism, the isomers can be called as dextrorotatory isomers or levorotatory isomers. Let us see what is meant by dextrorotation and what is meant by levorotation. So for that purpose we have to consider plane polarized light. Now tell me, what do you mean by plane polarized light? So when we consider ordinary light, it will have vibrations in all directions. When this ordinary light is passed through the Nicol prism, it is capable of absorbing all radiations in all vibrations except in one direction. So what is the purpose of nickel prism? It absorbs radiations in all directions except in one direction, and it is called as plane polarized light. So whenever this plane polarized light is passed through the organic compound, then there are two possibilities. Organic compound, if it is optically active, remember that if the compound is optically active, it can rotate the plane polarized light in clockwise direction or in anti-clockwise direction. If it rotates in clockwise direction, it is called as dextrorotatory compound and it is given with positive sign. And if it rotates the plane polarized light in anti-clockwise direction, and the isomer is called as levorotatory isomer and it will be given with negative sign. Is it clear about the dextro and levo rotations? So if at all the compound contains only one chiral carbon atom, if it possesses non-superimposable mirror images, that is called as optically active compound. For example, if the compound contains two chiral carbon atoms, then we have to test the compound for plane of symmetry. It should be devoid of plane of symmetry. Then only that compound is optically active. Is it clear about the optical isomerism? If the compound contains only one chiral atom, that will be optically active, undoubtedly. But if the compound contains two chiral centers, then we have to test for plane of symmetry. If it is devoid of plane of symmetry, then the compound is optically active. So if we consider the first example, here two chiral centers are present and this compound will not exhibit any plane of symmetry and hence it is optically active. And when you consider the second example, you just carefully observe the second example and it exhibits the plane of symmetry and hence it is called as optically inactive. So if the compound contains two chiral centers, we have to examine the plane of symmetry. If it is devoid of plane of symmetry, then the compound is optically active. If it contains plane of symmetry, and hence the compound is optically inactive. That is all about the optical isomerism. Let us consider the conformational isomerism. Remember that conformational isomerism arises due to the rotation around the C single bond C. Here, just by rotating around the C single bond C, we will get infinite number of isomers and they can be called as conformational isomers. And let us consider a simple example to know about the conformational isomerism, that is ethane. What is its molecular formula? C2H6 and the structural formula is CH3 single bond CH3. Here, to discuss in detail about the conformational isomerism, we have to write the spatial arrangement of this ethane. It is the front carbon atom and it is the back carbon atom. Here, if you carefully observe this isomer, the hydrogen atoms present on the front carbon atom are exactly superimposed on the back carbon atom and hence it is called as eclipsed form. So this form is called as eclipsed form. So front carbon atom, the hydrogen atoms present on the front carbon atom are exactly eclipsed on the back carbon atom and hence this form is called as eclipsed form. And by slowly rotating the second carbon atom, there will be infinite number of isomers are possible. So If we rotate around the C2 carbon atom, finally we are going to get a structure in which the hydrogen atoms present on the front carbon atom are far away from the second carbon atom, and the corresponding form is called as staggered form. Remember that staggered form is the stable conformation, whereas the eclipsed form is the unstable form. And while rotating the eclipsed form into the staggered form, in between we will get number of conformational isomers, and they are called as skew isomers. And remember that the stability of skew isomers is in between the eclipsed form and the staggered form. Is it clear about the conformational isomerism? How the conformational isomerism arises? Due to the rotation around the C single bond C, conformational isomerism arises. So eclipsed form is the less stable form, whereas the staggered form is the most stable form. In between, the number of isomers arises and they can be called as skew forms. Is it clear about the conformational isomerism and also about the isomerism, students? If you like the video, don't forget to like, share and subscribe. Thanks for watching. Have a nice day.